So what I want to do right now is I want to take the multi-segment coding style and the two-segment coding style, and I'll just basically use it to implement this particular circuit we have seen before. So let's go to Vivado and implement this, okay? All right, so what you see in here is that I opened a file and I called it FSM multi-segment because I want to implement the multi-segment parts. And just as a review, what I will do is I'll look at these segments and just put them as a code in here as a reminder. So what I'm going to do is I'm going to do maybe one, the state register or something like that. And number 2 in here, it's going to be the next state, okay, logic, and maybe number 3 here will be melee output. And this particular circuit I'm implementing, it actually have both melee and more output. So we do need 4 segment for it, okay? These are the more output. Okay, so let's get started. Well, first, before I actually get started in coding, what I need to do is I need to actually just make sure that my inputs and outputs are correct. So what I need to do in here is I need to say input logic, and of course we need a clock and a reset like any other sequential circuit. And the 2 inputs I have here, if I take a look at this diagram, you're going to see that I do have A and B as my basically inputs. Okay, so I'm going to have an input logic A and B, and input and output logic Y0 and Y1. Okay. Okay, so the inputs and output are specified. So before I start with the state register, what I need to do is I need to use the FSM data type, basically the one that we created a few seconds ago, or the, okay. All right, so the inputs and outputs are done. What I need to do is I need to create, before I start coding, I need to actually do the state types, basically the state type definition, the new data type. So what I'm going to do is I'm going to say, okay, let's type def enumerate, and what I have is S0, S1, and S2. I think this is what these particular states are called, so we're going to call it state type. Again, you can call them whatever you want. And then what we're going to be doing is we're going to do some signal declaration, okay? And that signal declaration, I'm going to say out of the state type, what I want to do is I want to do a state register that stores the current state of the finite state machines, and the state next is what it should be next. Basically, that will be the output of the combinational circuit. The combinational circuit will actually change that, and that's about it. So now the state register, if you take a look, well, we know that the state register should basically be it's a sequential circuit. So what we're going to be doing is we're going to do always FF according to the instruction. Okay, and we're going to say, well, it should be active at the positive edge of the clock like usual, and a positive edge of the reset because I need an asynchronous reset. So I'm going to do begin and end. And here I'm going to say, well, if reset, what I want to do is I want basically the state register, the current state register, to be S0. Basically, I want it to go back. This is my initial. Like, you can start anywhere, but let's assume that this is where we want to start. Okay, else we can do basically state register would be whatever is state next, basically whatever the next state logic decided, and that's basically the first part. So this here complies with the last guideline, which tells me that you need to separate memory component registers into individual code segments. Basically take out the registers out, and this is what we did in here. So we will go back in here. So the next state logic is actually what's more interesting, okay? Or this is where the meat is. And frankly speaking, it's extremely mechanical because all you have to do is just like take a look at what's happening in here with a bunch of case statement, well, with a single case statement and a bunch of if statements. You just need to follow that diagram. Whether you're following the ASM chart or the state diagram is pretty much the same thing. You're going to end up with the same place. So here, what I'm going to do is I'm going to say, well, always com, because this is combinational and this is my begin and my end. And then I'm going to say, all right, the case, well, let's test what the state register is, what's the current state is, and this is where end case is. Okay, and I'm going to say, well, I could be in S0 and I need to do my things, or I could be in S1 and I need to do my thing, so I could be in S3 and I need to do my thing. Okay, I don't think when you have S3, we have an S2. Okay, and then for default, what I usually do is I say, well, the state next, I usually do that is equal basically S0. Like this is if for some reason or another you ended up in S3 and S3 does not exist, let's assume, like the flip-flops or whatnot ended up in 1. You just have at least, you have a place to come back to. All right. So that's good. So let's see what's happening in S0. So you need to take a look at, well, whether you're actually looking in here or looking in here, it's pretty much the same exact thing. You need to test for A1, and then you need, if A1 is asserted, you need to test for B and so forth. So let's do that. So we're going to be doing a test for A. So I'm going to do if A. So if A is asserted, what do we do? Well, we're going to do the following. We're going to ask, well, if B. I'm going to actually ask for B. So if B is asserted, what I will be doing, I'm not going to output here because we're just doing the next state logic. This one is a multi-segment one. All it's dealing with is what should be the next state. And this, according to both diagram, the next state, if A is 1 and B is 1, is actually S2. Whether you do it that way, and you're going to tell me, well, if A is 1 and B is 1, that means I'm going to S2. So all you have to do is just tell me that basically the state next is just equal S2, and I have to use blocking assignment because this is a combinational circuit, and that's pretty much it. And then I'm going to say, well, what if B is actually negative? Well, basically deasserted. So instead of going to S2, what I will have to go to, I have to go to S1. So that becomes state next equals S1. All right, and that's pretty much it. Now I want to go back in here. I'm going to say, well, what if A is actually false? So this here tells me, well, you need to go back to the same state. So the next state basically is state next. Well, this has to be here. Okay, so state next has to be S0. This is why I'm saying it's mechanical, because all I'm doing is I'm following the ASM chart. So you do the design by hand, and then when you go to do the HDL, all you're doing is you basically are writing what you actually designed. So I'm gonna pause in here and just gonna write the rest. You can read it on your own, but it's pretty mechanical. So you get to see the whole code, right? Okay, so I wrote the case is basically the if statement for S2, just following the charts. And that's basically the next logic. So you can see that this segment just follows and tells me what the next logic is, and actually taking that next logic or next logic or state next, and the first part will actually update the current state. So what's left is actually the mealy output and the more output. So let's take a look at the mealy outputs. The mealy output is actually, I think it's just Y0. That's the only place where it appears. And it appears, it's attached to S0, A and B have to be asserted. So all I have to do is just say, okay, let's do the mealy output. And I'm going to say, well, I'm going to assign, and that was called Y0. I will assign it whenever state register is in S0. And B, A is asserted and B is asserted, and that's pretty much it. It will be asserted if you are currently in state S0, and A is asserted and B is asserted, and that's pretty much it. That's mealy output. Similarly, more output would be very, very similar. So I'm going to assign Y1 equals, I believe that should be, I'm testing whether you are in S0 or you are in state register. Basically, the current state is actually in S1. You're just testing, are you in here or are you in here? If you're in either one of these two states, I'm going to just assert it. All right, so take a look at this code again. This is why we call it a multi-segment. So it's called multi-segment because I have one for state register, one for next logic, one for mealy output, one for more output. It's pretty verbose, but it's very easy to debug and edit and understand. Okay, so taking a look now, what we did is we covered that. Now what I want to do is I just want to do the two-segment coding style, and the two-segment coding style tells me you put the state register alone, but then anything that is combinational, whether it's next state, mealy, or more, you're going to combine it. What's it telling me is, you see these code in here, the 2, 3, and 4. You probably could just do it. They're all sequential. They're all combinational circuits. You can just put them in a single block, single if statement, or whatnot. And that's what we're going to be doing next. So what you're going to see me doing is I will just copy my code in here, and I'll just basically paste it for my FSM, which is two-segment. Okay, it's the same input, same output, same state logic in here, same here, the same for the state register. What's different is now what I need to do in here. Now what I need to do is I just need to bring these outputs back in here. So let's start by bringing the Y0. So Y0 is associated with only state S0. So I basically have to edit the code in here. Okay, so let me just do this here a little bit more. So simply because probably I need to do other stuff. So we're going to do that, begin and end. And this is only done when both A and B are asserted. So I'm going to have to do this here, begin and end, because again, you need to use begin and you do need to use begin and end if you have more than one statement under each one of these if statements. So we're gonna do this. You can, it doesn't matter. So you can do that in here. We'll do say, okay, well, y0 has to be 1 bit and 1, and that's basically it. You're asserting it if it's in S0, A is asserted and B is asserted, you're asserting that output, and that's pretty much the meaty output. Okay, for the more output tells me, well, if you're in S0 or S1. So it's telling me, well, if you are in S0, what you need to do is you need to tell me y1 equals 1 and B and 1. Or you could be also in S1. So all you have to do now here is you're gonna have to add a begin and an end in here. Okay, and at the very beginning, you're gonna do y1 equals 1, well, 1 bit 1, and I think that has to be a 1. All right, and that's pretty much it. That saves it. However, one thing to keep in mind is the following. I am assigning y1 in here, and I'm assigning y1 in here, okay, but I'm not assigning it in S2. And let's assume that I am in S2. So what's happening is it will revert to the previous saved value. And the keyword here is saved, and I have an always combinational. So I need to fix this, because if I'm doing save, that means I'll end up with a latch, and Vivado is just gonna warn me that you're actually saving because you're not assigning y1 in all cases. So I can either go and make sure that y1 is assigned in each if and else statement, but an easier version of it is actually at the very beginning of the case. What I can do is, or at the very beginning of the always, actually, even before the case, I will always say y1 is deasserted. I can just basically say deasserted. It will be asserted if it's one of these cases in here, okay? So it's always 0 unless I specify otherwise. The same goes with the y0, because y0 is not assigned everywhere. y0 is assigned in here, but not anywhere else. So if I am in S1 or S2, it will revert to the previous saved value. So in order for me not to save anything, I'm just gonna assume that it's always 0 unless I change it. Okay, the same goes with the next state. So generally speaking, I think for the state next, you don't need it, but we just, like, for the sake of completion, just in case I forgot to do something somewhere, I'll just basically say, well, state next is, the next one is just going to be S0. And of course I'm changing it everywhere, but just in case I just forgot it. And that should be the same. And of course, if you compile, if you synthesize both of these codes, whether the multi-segment or the two-segment, you should get the same exact circuit, okay? You're describing the same exact finite state machine. Nothing has changed. Okay, and this is basically how we code finite state machines, multi-segment or two segments. The one segment tells me you can always also combine these up in here, but it might be a little bit confusing because you have some non-blocking assignments. So all of these have to change to non-blocking assignments, and you have to figure out the effect of that, changing these to non-blocking assignments and putting them there. So I'll not do that. It's more complicated than it should be.